yesterday. And in those problems, you'll notice when it always says a gas, blah, 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 blah. What is the new volume? Or what is the new pressure? Or how much, if the new volume of the container is such and such. And so the way these are known as empirical gas laws work is it's always asking you, what is something if you change something? Okay? We're going to deal with a different kind of problem today. It's called the ideal gas law. And in the ideal gas law, in essence, you have PV is equal to NR. PV over NT is always equal to this value. So this constant is always the same regardless of what the gas is, what the volume is, what the pressure is, what the moles are, and what the temperature is. So it's always that constant. And so they call this the ideal gas law constant. And that's the value you'll need to know. On a test, I'll give it to you. I'll also give you equations on the test. So like this equation and the equation we used yesterday, I'll give you those equations. I'm not going to ask you questions like, what is Boyle's law? Okay, I want to ask you, what's Avogadro's law? I want to ask you what, there's a bunch of them, right? I don't care that you know particularly which one is which, but I care that you know what the relationships are. So pressure and volume, if the pressure goes up, right, the volume goes down, that kind of stuff. So those are the things I expect you to remember. All right. So let's look at how we use this equation. Now, the thing I always want you to remember is R is equal to 0.0821, and then the units are liters, atmospheres, over moles, times Kelvin. And here's the deal. Those are the units you have to use in the calculation. So if you don't use those units in the calculation, then the answer is not going to come out right. Okay? So it says a solid and I don't know why it says a solid, but it does. A 600 milliliter container at 70 degrees Celsius and 0.95 atmospheres contains helium gas. How many moles of helium is in the container? Should be R, huh? That bugs me. That's okay. How many moles of helium are in the container? So let's look at the equation. All right. I have a P, a V, an N, and a T, and R is already given. So you notice, what's this? 600 milliliters. That's my volume, yeah? So what I usually like students to do, I think it helps, is do P, V, N, and T. Just write that down. And then that's 600 milliliters. Oops, wrong place. 600 milliliters. What's the 70? That's T, so it's going to be 70 degrees Celsius. Now look over here at K, right? The units, right? It's K, right? It's Kelvin. So this temperature has to be done in Kelvin. This is milliliters. What does it have to be in? Liters. So we're going to have to do all these conversions, right? So for this one, it's pretty simple. It's 273. I have to add 273. The Kelvin temperature is always 273 degrees higher than the Celsius temperature. Well, what else do I have here? I have 0.95 atmospheres. That's this guy here. What am I looking for? All right, moles. So take your equation, you solve it. And that's what you'll have to plug in. Okay. So only thing I have to do is convert oops, I ran out of space. 0.6 liters. Get this guy back there. There. Milliliters will cancel out. I'm assuming you do the dimensional analysis thing where you cross out units. Yes, no? Was that familiar? That's familiar? Yeah, okay, good. Remarkably, some people don't do that. And I'm just like, well, how do you get through life? You'll find out, like, I should bring my wife in. She likes to talk about dimensional analysis because she's my wife. And she will tell you that one skill got her through chemistry and physics. So like when you take college physics, one of the things you have to be able to do is deal with units all the time. If you can't remember an equation, sometimes you just look at the units and go, that's the equation, and then you go from there. So it's pretty awesome. Okay. So now I have all my units correct. I have atmospheres, liters, and I have Kelvin. That'll be 343 Kelvin. So then I can just plug stuff in. So P is 0.95 ATM. And V is 0.6 liters. That's an L. And then, let's see, R is 0.0821 liters times atmospheres over moles times Kelvin. And T is 343 Kelvin. And then just to look at this, if you look at the units will cancel out. Atmospheres goes here, liters, Kelvin, and then you have a 1 over 1 over. You guys remember that from math? 1 over 1 over? You just invert. So that's 1 over 1 over moles, so that becomes moles. You stick it in your fancy calculator, which I will use my phone against. So let's see, what does it say? 0.95 times 0.6 divided by 0.0821 divided by 343. And that becomes 0.0202 moles. By the way, keep your calculators out. When I do these calculations, try punching them in, because if you're not getting the answer, then we can stop and we can say, like, because you're probably not doing anything wrong here. It's probably just a calculator thing. And I will tell you, like on my first exam in the summer, almost always, because we do a lot of dimensional analysis, people will punch stuff in wrong on their calculator. And I'm like, well, it's set up right. How did you get that answer? And then they show me what they did, and I'm like, oh, well, you should have put parentheses on this, or you should have. It's an easy thing to solve, okay? So make sure you get your calculators out and give it a shot. And I'm going to go ahead and punch that and see what you get, and then we'll do the next problem. Sorry. I got used to getting up at like 7:30 instead of 6:45. It's a big difference. I feel for you guys that go to school every day at 8. My classes start at 1. It's nice, right? I have to go late though, because I have a job. All right, you guys getting the answer okay? Huh? Okay. If you're not, and if you don't want to say it out here, that's fine. But these are all friends, so they'll be nice. They better be nice. Yeah, talk it through with your friends if you're not getting it. All right, we're gonna do. Did you get it? Yeah, you got it right. Figured you got it. What's your shirt say? Chicago? Chico State? It's a good school. You guys any have college plans already, right? You all plan to go somewhere? Yeah. Go somewhere. My first advice to you, if you can, get out of here.
Yes. Yes.
I would not have said that except for that's what I did. And it's a whole different, I went to Santa Cruz, but then I went to Indiana, and then I went to North Carolina. You just get to see a different part of the country, and then you get to restart yourself. You get to think to yourself, I'm going to be a better student, or I'm going to do this, or I'm going to do that. And you don't feel that outside pressure to be like a certain person, and so you get to be yourself. So just 2 cents. Okay, having said that, we're going to do the next problem. Reading the problem says 12.4 liter container contains 6 grams of methane at 10 degrees Celsius. What is the pressure? So it's not asking you what the new pressure is. It's not asking you after you change something what things are. So this is a Puvnert. This is what people usually say. PV equals nRT. Puvnert. So we're going to go P, V, N, and T, and I'm writing in green. I'll change it back to blue. Sorry. So what's the pressure? Answer is, don't know. That's what I'm trying to find out, right? V is what? Okay, so 12.4 liters. N is, yeah, so he's, what is N? 0.375 moles. How do you get that? You have to start with the grams, right? So he started with his grams. Right, let me actually write the whole problem out. It's 6 grams. And this is what you have to remember. 6 grams, that's the quantity, right? So that's what's going to become the moles. Let me move that out of the way. And then he calculated the molar mass of methane, which is about 16. Is that what you got? Yeah? 16.04 grams or 5. Yeah. Grams for every 1 mole of CH4. And then he got 0. What'd you say? 0.375 moles. And then T is 10, right? But it's 10, and we need it in Kelvin, so we had 273. So that's 283 Kelvin. So we got everything I need. And so just remember R. I know there's a saying about a dead horse. You know, there's an old saying about a dead horse. You don't know the saying? Something about beating a dead horse. Don't beat a dead horse. It's kind of a mean saying, but I'm just going to keep saying these are the units of R, even though you kind of know the units of R probably, because that's what your units have to be in. But when I do this calculation, what are the units I'm going to get? For pressure. It'll come out as an ATM, but what's the question asking for? Millimeters of mercury. So you're going to have to convert the atmospheres into millimeters of mercury, thinking ahead in the problem, right? So we'll go ahead and calculate P, knowing that it's coming out in atmospheres and knowing that we'll have to do the conversion from atmospheres to millimeters of mercury. So, what is it? nRT over V, right? And so I'm going to plug in. This is down here. I'm just too lazy. I could have written P easier than that, but whatever. 0.375 moles times 0.0821 liters times atmospheres mole time Kelvin. You think you're tired of writing that unit? Can you imagine doing it for like 25 years? You're not even alive for 25 years, right? Yeah. It's kind of like, though, just rolls off your tongue after a while. You don't even think about it. Like Pavlov's dog. Do you know Pavlov's dog? You guys don't know Pavlov's dog. You guys don't know Pavlov's dog? What do you guys do in life? Oh, Pavlov's dog is great. Pavlov was a behavioral scientist, a psychologist. He trained his dogs to salivate when he rang a bell. So he would feed them and ring a bell, feed them and ring a bell, feed them and ring a bell, and then he'd ring a bell, and the dogs would salivate, but they wouldn't get any food. Yeah. And everybody would laugh at him until the lunch bell rang, and then, never mind. Lunch bell rang, and they all salivated, right?
Oh.
But wasting some of my best jokes. Divided by, 12.4 liters. Somebody must have done the calculation by now. What'd you get? What? Because it's, 283. Sorry, 283. I'm used to doing like hundreds of degrees. And what'd you get? 14.475 ATM. But the question asked for millimeters of mercury, so we can convert that over. It's 760 millimeters of mercury per 1 ATM. Now those kind of conversions will be given to you. You don't have to memorize those things. Unless you want to, and then that's fine. It's up to you. All right. Wow, that's a big number. What'd you get? I don't know. I just asked you guys, and somebody told me. Is that not what you got? Because I thought that's a lot of pressure. Okay, so no, they didn't lie. The calculator lied. You should remember that in life. Just because it looks good doesn't mean it's telling you the truth. Is that bad? Should I not say things like that? It's okay. Yeah. I say stuff that to my little kids and they don't get it at all. I'm like, that's good. That's how you check. Like, what do they know? What'd you guys get? 0.7027. That sounds nicer. All right. Do I have to run this myself? I'll tell you. What? Yeah, I got the same number. Good. That's in atmospheres. And then it's 760 millimeters of mercury is 1 atmosphere. And so that's 534 millimeters of mercury. There you go. All right. Questions on those? Pretty straightforward. Look at the numbers. Make sure they're all in the right units. Plug and chug is what they say. Just stick them in there and start hitting your calculator buttons. Just make sure the units are right. Otherwise, chaos will ensue. So you can do stoichiometry problems with gas laws. So we're going to use the ideal gas law to calculate moles, or we'll use gas volumes to calculate moles using the ideal gas law. And so it says, how many milliliters of hydrogen gas can be collected if 9.2 grams of aluminum reacts with an excess of HCl at 20 degrees Celsius and 730 mummahugas? I learned that from a student, and it stuck forever. I can't get it out of my head, so I just wanted to say it once. And now I'm done.
I didn't hear you say that.
Mummahugas. Mummahugas. Like you're hugging your mom, right? Mummahugas. Yeah, now you can just think that. So, okay. So let's look at this problem, right? You have grams of aluminum. You have a temperature and you have a pressure. If you see temperature, pressure, mass, moles, something like that, your brain should go ideal gas law. It should just do that, okay? And it doesn't do it right now, but it should. And so you're going to write out, right, from this, you're going to have aluminum is 9.2 grams. And I have I'm going to put PV equals nRT over here now. I have that on this side. And so I have to start putting this together. I have a pressure that's 730 millimeters of mercury. I'm looking for a volume, right? And I have a temperature. So I have 20 degrees Celsius, and I'll just add 273, so that's 293 Kelvin. So you notice I'm missing two things over here? And I'm looking for the volume, so that means from the aluminum, I should be able to pull out the moles. So I just set up like what, I know it's ideal gas law, it's probably one of those problems. I set up PV equals nRT on the right-hand side, I filled stuff in, and then it tells me, oh, I have to have moles because I'm looking for my volume. This needs to be moles of what? In the moles of hydrogen. No, it needs to be moles of hydrogen gas because it's asking how many milliliters of hydrogen gas. But I was given aluminum. This is where the stoichiometry comes in. I'm going to take the grams of aluminum. I'm just going to write the little map here. Grams of aluminum, moles of aluminum to moles of hydrogen. And once I have the moles of hydrogen, I can stop. Because that's what I need to calculate its volume at those conditions. So I'll just plug that in. You guys see how I did that? All right. I just laid out everything that I had. This is what you should do in a problem. Identify all the variables you're given, and then look for the relationships between them. So, in this case, the moles of H2 is going to be 9.2 grams of aluminum. Molar mass of aluminum, 26.98. And then I need my mole ratio between aluminum and hydrogen. So there's 3 moles of hydrogen for every 2 moles of aluminum. Or aluminium. Sorry. So 3 moles of hydrogen for every, and this is Al here, sorry, I forgot it. Every 2 moles. So plug it in and let's calculate. So 9.2 divided by 26.98 times 3 divided by 2. 0.512 moles. Now I have to do the ideal gas law part, right? And I can plug this value in here now. That's the value I just calculated. I put that all the way off to the side, a little bit too far. Hang on. This is moles. Now, what's wrong with my pressure? Wrong units, right? It needs to be an atmosphere, so that conversion has to be done. This is the one drawback to doing all of this on one screen with somebody else's notes. I thought there was enough space here, but there isn't quite. Okay, so we'll do that calculation. We'll just plug it into the equation. I am going to do the rest of it just down here because I'm pretty much out of space there. Okay, so looking for volume. nRT over P. So 0.512. Oops, look at that. I'm out of space already. I'll do it here. 0.512 moles. R 0.0821 liters times atmospheres over moles times Kelvin. I'm out of space. I'm going to insert a number here. And the Kelvin's 293 Kelvin. So that's all multiplied together at the top. At the bottom, I need to put my pressure in millimeters, or in atmospheres. So 730 divided by 760, and that's 0.9605 ATM. And now I can just plug all that in and calculate. 0.512 times 0.0821 times 293 divided by 0.9605. Yeah, that seems reasonable. 12.8 liters. Okay? And, just for form, the Kelvin canceled here, the moles canceled here, the atmosphere's canceled here, and I'm left with liters.
Will we need to know the pressure conversions on the test?
Nope. I'll give you R, I'll give you 760, 1 atmosphere, 'cause 1 atmosphere, I'll even give you PSI, but we're not using that.
What's STP?
We're getting here. That's the next part, right? Do you guys remember what STP means? Standard temperature and pressure.
Right, but what's the value?
What's the value? 22.4 liters is equal to 1 mole, but he wants the temperature and the pressure. What's the standard temperature? 0. And what's the standard pressure? 1 atmosphere. 760 millimeters, yeah. So if you forget the 14.2, or 22.4, sorry, 14.2 is something else. 22.4, if you forget that, you can always calculate it using the values for STP. You can plug in that temperature and that pressure and you'd be good. Okay, am I done with this answer? No, what's it asking for? Milliliters, right? So there's 1,000 milliliters. I expect you to know the milliliters to liters conversions. Is that something they're expected to know, Dan? Is that milliliters to liters? They're expected to know that, right?
Yes.
Yeah, okay, good. Because I'm not going to tell them that. So the 1,000 milliliters is in 1 liter. I don't know how that got explained to you, but that's 1280. 12,800 milliliters, like that. All right, so STP, we talked about what standard temperature and pressure were. It turns out that 1 mole of any gas has a volume of 22.4. And some people know the 4-1, like 4 sig fig version, and some people know the 3 sig fig version. Do you guys know which one you know?
3.
The 3? Okay, so we'll stick with that. I'm just kind of guessing at like how many sig figs you know things to. I'm just kind of going with it. 22.4 liters. So that's what a mole of gas is equal to in its volume at 0 degrees Celsius and 1 atmosphere pressure. So it says 100 mils of hydrogen gas, right? How many grams of aluminum are required to produce 100 mils of hydrogen gas at STP? And so what we're going to do is we're going to do the following conversion. We have 100 milliliters of hydrogen. We're going to use this, which is known as the molar volume of a gas. And we're going to convert that into moles. And then once we have that in moles, we'll use stoichiometry to figure out moles of aluminum. And then grams of aluminum from there, okay? I like to just string all these things together. I don't know how you guys do it, but that's what I'm going to do. Well, 100 milliliters. Now, if I want to use the molar volume, what are the units for molar volume? It's moles and liters, right? So the 100 milliliters has to be converted over to liters so that I can use it. So it's 1,000 milliliters is in 1 liter. And then I know it's 22.41 liters is 1 mole of hydrogen. So if I'm looking at my units right now, I have hydrogen. I have moles of hydrogen. All that gives me moles of hydrogen. And then what's the next thing I need? For moles of hydrogen, I need to go to moles of aluminum. And once I have moles of aluminum, I'm going to get grams. Okay? How do I get to moles of aluminum? What? Mole ratio? Yeah, mole ratio. So 3 moles of hydrogen at the bottom and 2 moles of aluminum at the top. And then I'm going to get it over to grams, and it's 26.98 still. for every 1 mole. And then I can see all these units cancel out and leaves me with grams of aluminum. So now I just need to do it on my calculator. I have a number. I could be right and I could be wrong. What'd you guys get?
I got 0.08.
0.08. Could be right. I got it. That doesn't necessarily mean that you're right. Anybody else get it? 0.08? All right. 3 people, we can have an agreement. So the grams of aluminum, 0.080, roughly grams. That kind of makes sense when you think about it in the big picture, because 22 liters, right, is 1 mole. So it should be really a small fraction of a mole, so that means the mass will be pretty small too. So it kind of makes sense. All right, so 1 more section to cover, and then we're going to go on into the next chapter. I believe the exam on Thursday is through chapter 12, and this is chapter 11, so we need to finish this in the next chapter as well. Today's experiment, by the way, is like super short, so cross our fingers, we'll be done and out of here early. Well, okay, you guys are stuck here. So, but I'll hang out with you. I'll hang out with you and help you fix these. I'll sit down and we'll fix them. Okay. All right. Any questions on what we've done so far? New topic. Okay. What's 1 plus 1?
2.
Whoa. That would have been funny. I'd have been like, "You're fired." I pay people in candy, so I haven't gone to the store recently, so I don't have any candy. You just have to get paid on goodwill. All right. So that kind of makes sense, right? 1 plus 1 equals 2, because that's arithmetic. You just know that. So if I take a liter of water and a liter of ethanol, think about this. I have a liter of water and a liter of ethanol, and I pour them together. So I have 1 plus 1. It's not equal to 2.
But you have 1 liter of...
Yeah, you have 1 liter of a liquid and another liter of a liquid. You mix them together. The volume's usually about 1.8 liters if it's pure ethanol. What? Where did all that stuff go? That's like 200 milliliters. That's like a cup gone.
Well, is it closed system?
Huh?
Is it closed system?
Closed system. Where'd it go? Is there a hole in the bottom of my graduated cylinder? Where does it go? They like each other. And so what happens is the molecules get closer together. The liquid becomes more dense. So here's the thing. When you talk about gases, right? What did we say about the properties of gases, like kinetic molecular theory? One of the things we say is that gases have no attractions, no intermolecular forces with other gas particles, and so they don't like each other. So it turns out if you take 1 liter of a gas and 1 liter of a gas, and you don't change the pressure and temperature, you'll get 2 liters of gas. It kind of works out that way. Now, that's a law known as partial volumes, and we don't deal with that one in this class, but we deal with something called partial pressures. Okay, so let's say I have a container, right? And inside the container, I put 300 millimeters of mercury, because I like saying millimeters of mercury, of, let's say, oxygen, and then I put in 700 millimeters of mercury of, what's your favorite gas?
Nitrogen.
Nice. That's a good one. All right, just not say that. What's my total pressure? 1,000. Just adds. It's really nice. It's 1,000 millimeters of mercury. Just add them together. Add them together. And this is known as the partial pressure of nitrogen. This is not a slide, I just added. And this is the partial pressure of hydrogen. And sorry, I can't let that one go. Looks weird, but it's right. So, yeah, it's just called the partial because they're part of the total. That's all. So people freak out about the word partial pressure. Like, I don't know what a partial pressure is. It's just part of a total. Okay? And it's as simple as adding up the pressures to do these problems. Okay? So, I don't know why there's 2 blank slides. First problem. Container contains 3 gases with a total pressure of 700 millimeters of mercury. One of the gases has a partial pressure of 200. Another of the gases has a partial pressure of 400. What is the partial pressure of the third gas? So I'm going to show you how you write it out. Like Dalton would have written it out. He would have said pressure total is the same Dalton, atomic theory Dalton. Pressure total is equal to the pressure of the first plus the pressure of the second, okay, plus the pressure of the third. And so he would have said pressure of the third is the pressure total minus P1 minus P2. That's all he would have done. Just subtract them all. I mean, you kind of know that from what I told you. Yeah. I'm just showing you what Dalton would have done. And so that becomes what? 100 millimeters of mercury. Okay. I know it's disappointing. Like, couldn't it be harder? I want to show you one other thing. It's not in these notes. I'll just slide up to this blank that I have up here. What is the composition of air? What are the 2 most common or most abundant gases in air? Nitrogen and oxygen, right? So it's like 20% oxygen. It's about 78% nitrogen. All right? It's like, doesn't add to 100, right? There's other gases in the air. Do you know the third most abundant? Who knows it?
Nothing.
Huh? Methane? No, only a group of boys like this, but yeah. That's, never mind. You got it? She got it. Methane, never mind. What's the third most abundant gas? Argon. Right? Like argon, the noble gas, argon, this guy that's over here. Yeah, the third gas is argon, and I forget what it is. It's like 1% or something like that. And then there's other gases. But you don't think about argon being there because no matter what you do, it never reacts. And so it just sort of sits there in a volume of gas. In fact, that's how they discovered argon. When they were trying to figure out what air was made out of, they figured out how to react all the oxygen off, figured out how to react all the nitrogen off, and there was always this little bit of gas left. And they're like, what's this gas? And they tried all kinds of stuff, and so finally a guy in England, what's his name? He got the Nobel Prize for this stuff. Determined that there was an inert gas, and he asked his son, actually, his little boy, he asked his son to name it, and of course his little boy knows Latin. And so he names it, yeah, right? Different era. I barely know English. He named it argon because argon means the lazy one. And so he couldn't get the gas to react. So the son said, well, that's obviously the lazy one. And so that's how it got its name. You guys know how helium got its name? Because he named helium too. Helium, when they took helium and they did you guys do the atomic spectroscopy lab where you got to see the lines? The electrified gases? No, you didn't do that one? If you electrify a gas, you can create colored lines out of it using a spectroscope. And when you did helium, it created the same colors as the sun. And helium stands for Helios, which is the sun. So, yeah. How it's originally discovered. They actually collected it from radioactive isotopes decaying, and helium is a byproduct of the radioactive reactions, the nuclear reactions, and so they collected it up and said, what is this weird substance? And that's how they got helium. Kind of cool, huh? Yeah. All the same guy. Okay. So, we're going to do a collected over water problem. When a gas is collected over water, there is always water vapor above the water. So there's always a partial pressure due to water. Okay? So like if I have a container and I collect a gas in it and there's water in that container will contain the gas I'm collecting plus water vapor. So by Dalton's law of partial pressure, we would say the pressure total is the pressure of a gas, whatever you're collecting, plus the pressure of water. Oh, sorry, I was going to put P there. I'll put W instead of H2O. So if you want to know the pressure of the gas, you collect it, and then you just subtract the vapor pressure of water from the total, and that's how you get the pressure of the gas. Okay? Now it says, the gas is collected and allowed to sit to reach equilibrium. The pressure of the container would be the same as the atmospheric pressure. That's kind of partially true, but that's all right. Now, I'm going to, and this is just what I wrote up there. We're going to do this. This is what the collection device looks like often. We're collecting. We have a reaction on the left-hand side, zinc and hydrochloric acid. It produces hydrogen gas. The hydrogen gas is collected by inverting a bottle and running a tube up underneath it. And so as the hydrogen gas goes up into the bottle, the water level drops. And the gas that's the top, this is H2O plus hydrogen. So what that means is that the pressure inside that container is the pressure of hydrogen plus the pressure of H2O. Now, here's the only catch. The pressure of water, the vapor pressure of water, and you kind of know this, as temperature goes up, the vapor pressure goes up. All right. Like if you take a shower, and you take a hot shower, right? And there's steam everywhere. Why is there steam everywhere? Because the hot water has a much higher vapor pressure than cold water, and that as that water vapor hits the cold air, it condenses and produces steam. That's what the steam is. It's like fog that you're making in your bathroom. But at low temperature, like take a cold shower, which, on the summer day, that's what happens a lot. The water vapor pressure is a lot lower. So what they've done is they've tabulated or made a table the vapor pressures of water as a function of the temperature. And usually they do these in millimeters of mercury because in atmospheres they're really small numbers. Questions on that? So if I make I was going to do a demo. I'll come back and do the demo right after we finish this section. We'll take a break and I'll do the demo. Do this problem. Hydrogen gas is collected over water. By the way, I like abbreviating. So hydrogen gas is collected over water in a container at 25 degrees Celsius when the atmospheric pressure is that. If the vapor pressure of water is 55 millimeters of mercury at 25 degrees Celsius, what is the pressure due to hydrogen? Is it actually that? It doesn't exactly say, huh? Close. Hang on. It gives 20 and 30. I don't think that's right. Anyways, that's fine. Pressure total? That's 780. Pressure of hydrogen is what I'm looking for. And then I have the pressure of H2O. This number is apparently 55 millimeters of mercury. So that means pressure of hydrogen is just 780 minus 55. Just subtract. I don't know what I'm doing find this on a calculator. Okay, 725. Do a little side note, just for the demo. Well, you'll need to know it soon anyways. But little side note's this. If I graph this data, right? I put temperature on this axis, and I put P of H2O on this axis. It looks like a curve. I don't know if you notice. At low temperatures here, it's starting out at low pressure, and then it goes up. But you know, it's not going up evenly. It's going up exponentially. Like these are 10-degree increments, and between here and here, it only changed, you know, about 8 degrees. But between here and here, or here and here, it changed by a much larger amount. And so actually what this curve looks like is it looks like this. It's exponential. And so, at 1 atmosphere, this temperature, so when the partial pressure of water vapor is 1 atmosphere, this temperature is 100 degrees Celsius. That's the boiling point. This is what we define as the normal boiling point of water. And we're going to use this in the demo that I do next. Have you guys seen the collapsing can demo? You guys see that one? Yeah, we're going to do the collapsing can. I have it all set up. I just didn't bring it. Okay, so that is it for that chapter. It's weak, moderate, and strong, and we'll go through and talk about what the weak, moderate, and strong intermolecular forces are in this lecture, and how they have the effect on properties of materials. So you're going to learn about different properties of solids and liquids, and how that's related to the attractions between molecules. So first of all, let's just review real quickly. Physical states of matter, the solid, liquid, and gas, right? Solid has a fixed shape. Volume is fixed. It's not compressible, and it doesn't flow, because if it was flowing, what would it be? A liquid, right? Yeah. It's a solid, right? So these are solid. These are solid. This is liquid. I left it all over the table. So liquid, the shape is, it says indefinite because it flows, right? Property of one of the names for liquid, another liquid term, is called fluid. And a liquid will flow, or his fluidity will flow around an object. The volume is still fixed. So regardless of the container that it's in, it'll still have its same volume. You can't compress it, and it flows. It has fluidity. Now, a gas, we just talked about this. The shape is whatever the shape of the container is, indefinite. Volume, it can be any volume. So if I take a mole of gas and I release it into a room this size, it'll fill the entire room. But if I release it into a room the size of, let's say, what's that Bulldog basketball place called? Called arena. Yeah, it's arena. Release it, it'll fill the arena, right? So it fills whatever. The volume of a gas is just whatever the container size is. What? You're having a good day, huh? Yeah, you guys are all giggling over here. Is this every day?
Yeah.
So far? It has been every day. I'm okay with it. I just get, it's more opportunity to stare at people and pick on them. It's okay, right? You guys are okay with that, right? No? Yeah. So like, no, yeah. All right. So you can compress a gas, and a gas will also flow. All right. You guys all know those?
Yes.
Those are testable questions, right? I'll just ask you random things. Good.
Okay.
In terms of structures, right? The solids may be the easiest to understand. There's different kinds of solids. There's crystalline solids and amorphous solids. It's an N. It doesn't look right to me now. And then amorphous. This is an example of a crystalline solid. What do crystalline solids make? Crystals, right? So like salt crystals, sugar crystals. Crystalline. Yeah. Oh yeah, I left some letters out. It's right enough. Crystalline. Yeah. And then amorphous. Amorphous means doesn't have a regular repeating pattern. So if you look at a crystalline solid on the atomic level, it's made up of little cubes usually, or little hexagonal shapes. It's made up of a crystal lattice and has a regular repeating pattern like this solid does. And amorphous solids lack that. So if you have a crystalline solid, one of the things that's characteristic of a crystalline solid is that when it melts, it has a single melting point. So things like ice melts at 0 degrees Celsius because it's a crystalline solid. Salt will melt very close to a certain melting point. I can't remember what it is, but it's like 500 something degrees Celsius. It has a melting point, but it's fixed. Amorphous solids tend not to melt at a single temperature and tend to get soft. So name something that when you heat it up gets soft.
Starburst.
Yeah. Starburst. You guys make the Starburst sandwiches and you roll them flat, right? The reason Starbursts do that is because it's not a crystalline solid. If you took a Starburst and you try to do this and they turned into a puddle into your hand, like immediately, that would be an indication that it was crystalline. But things that are amorphous just get soft before they melt. So what else? I like that one.
An eraser.
Chocolate, kind of, but it's a mixture. More of a mixture. Now, it's something you eat food. What about, have you ever been to the fair? And you've seen the guy making the little horses out of glass? Or the little, what? Oh my God. Well, next time you leave your cave, you should try going and see some of
Oh
these.
wait, I spent a long time at the fair. Please tell me where this happened.
It's usually at the entrance to a tent. Like you go into a tent, there's this guy, and he's got these weird goggles on because you can't, if you look at heating glass too long, it'll burn your retinas out. And he's there, and he's making little objects out of glass. Well, glass turns out to be amorphous.
Wait. What?
Yes, glass is amorphous. It's constantly, it's, it,
Glass blowing glass.
Yeah.
yeah, so when you blow glass, right, if glass was crystalline and you got it to its melting point, it would just melt. But glass gets soft. And so it's,
Oh
it's
yeah.
cool.
That's how. Is that how they do like the glass?
Oh, yeah.
Where you heat it up and like you can like change the shape of it.
Yeah, that's what the glass blowers do.
I
I
love
watched
it
those.
too.
Okay, enough of that. So, it is interesting though, right? Just knowing that it's structurally, it's not like this. It's random. It's got a random shape to it. Okay, so then liquids and solids are similar in that the molecules or the atoms of the liquid and solid are close together. But the liquid at the same temperature would have weaker forces of attraction in it that allow the molecules to move around each other. In a crystalline solid, the forces of attraction are very uniform and strong. And so it holds it together in that crystalline shape. And for gases, they have no attraction, so they just fill whatever container it's in. Okay, so in terms of intermolecular forces, right, gases and their properties, gases have the weakest intermolecular force. So a gas has the weakest intermolecular. This is the middle stuff's all the stuff we've seen already. The liquid is a little bit stronger. It's holding the molecules together but not holding them in place. Okay? And a solid has the strongest intermolecular force. And as a result, the atoms or molecules of the solids can't move freely around each other. Now, I will say that at the atomic level, if you look at the surface of a solid, the atoms are actually moving around, but inside the solid, they're not moving around. Okay? So, yeah, if you actually blow up like a piece, take gold, and you look at it on the atomic scale, you can actually see the atoms moving around.
What?
Is that what gives it like its malleable properties?
It's part of that, yeah. But yeah, part of my research as a postdoc was to look at gold surfaces. And you take a picture of a gold surface using a scanning tunneling microscope, and you come back, and you take another one, and like everything moved, and you're like, dang it, because you didn't want it to move. You wanted things to stay in place. But it was really cool. It was fun to watch. Let's put it that way. In a mesmerizing, sort of hypnotic way. All right, so we're going to talk about phase changes. Let me sketch out the phase changes for you really quickly. I'll do it right here. We have solid. What else do we have? Liquid. All right. I'm going to draw them in a vertical like this, and the top one is gas.
What about plasma?
Okay, plasma. Want another one? There is another one. Bose, like the stereo speaker, but not the same Bose.
Is that like
There's another one now.
Okay, listen, how about we just keep it?
We're just gonna stop with this thing. Okay. So we don't care about these bottom ones and this top one. Plasma is the sun. Plasma is at very high temperatures, and the Bose-Einstein condensate's very low temperatures. The way I've got these things organized, and like in a Chem 1A class, we would go through some of these. But like the way we have these organized is this is energy going this way. So that's increasing energy. Zoom a little bit. Increasing energy going up. You should read about the Bose-Einstein constant because it's really neat.
I was just about to ask, what is that?
I can't tell you right now, but I'll tell you in a second. Okay. Right. And I might just slip it in somewhere, so. Okay, so that's increasing energy. So going between a liquid and a gas and a liquid and a solid, those are what we typically refer to as changes of state. Okay? Now, for melting, right? What is melting? That's what's transition. That's going from the solid to liquid, right? So I'm going to go like this. Like from here to here, that's melting. What's freezing? Yeah, it's the same transition going in the opposite direction. And conservation of energy says that that amount of energy is exactly the same. Like if you wanted to freeze a mole of water, it would take 6 kilojoules per mole roughly. And then if you wanted to melt it, it takes 6 kilojoules per mole. And the energy difference is the energy difference between the liquid and solid state. The temperature remains constant. It's just that in the liquid state you have more energy. And that's why they're allowed to move around. So you're putting energy into it, you're increasing their kinetic energy. The kinetic energy is the motion of the molecules. So melting's going up and freezing's going down.
Are there any other materials that get less dense as they freeze?
No.
Ice is
Isn't that weird? Ice is the only one that gets less, as far as I know, is the only one that gets less dense. And it's because of its hydrogen bonding. Remember that? Yeah, good. It is really pretty fascinating, actually. You know there's like something like 8 or 9 phases of ice at high pressure? Like, yeah. There's all kinds of stuff that's real interesting. Like if you dig into it, you just find out like, what you find out is you found out you didn't know anything. And you'll be like, well, that's really cool. Now I know something and I'm really smart. And you'll read some more and you go, I didn't know anything. But that's really cool. So let's see what I can find out. You can just keep doing this forever. And it's not a TV show and it's not a movie and it's not a web page. Not a game on my phone that keeps telling me I have to go do something. I actually have those. And I wasn't kidding about Pokemon. I play Pokemon too. I ride my bike everywhere. I don't actually drive a car, so I just ride my bike. And so when I ride my bike, I play Pokemon Go. All right, so right, I went to Santa Cruz. I'm kind of like a hippie.
Wait, I love that.
You like my shirt, by the way?
You drive your bike,
You ride your bike?
and don't drive.
On your phone?
Wait.
Yeah.
Wait, do you live here in Wheatley?
I live in Reedland.
Oh.
Well, yeah. But see, I have a little holder for my phone, and it just sits up there. And I listen to music or books.
That's lovely.
I'm going to be one of those crazy guys when I get older. I'm not older yet. Okay, back on task. Back on task. Okay, so what's the phase transition between liquid and gas? You guys know? Huh? Not sublimation. Liquid to gas is? Huh? Evaporation or vaporization is the word that we'll use. So this is vaporization because you're making it into a vapor, a gas. So vaporization. It takes, for water to at its boiling point, it takes about 40 kilojoules of energy to get 1 mole of gas into the gas state. So it's quite a bit of energy. What do we call the reverse process? Condensation, yeah? I'll just say C-O-N-D. Because of condensation. Now, 2 others that we need to worry about, or you don't need to worry about, but you should know, is when you go from solid to gas. That was sublimation, because it is quite sublime. It's what happens in your freezer, by the way. You know, if you stick a piece of food in the freezer, it's been there too long, and then you open it up and it's all weird and dry, that's because of sublimation. That's because the frozen food, all the water that was in it goes to the gas state directly without ever thawing. Okay, it's also the reason we call dry ice is right. You knew that was coming. The dry ice is dry ice because you go from the solid CO2 to the gaseous CO2 without ever going through the liquid. Now you can get it to be in the liquid state, which is also very cool, but I'll talk about it some other time. What is it called going this way? You guys know?
Going which way?
Going down from the gas directly to the solid. Because that's where all the ice crystals inside your freezer show up from. Like you open up your freezer, water vapor goes in, you close it, and when you open it up next time, there's all these little hairy ice crystals everywhere.
Oh, yeah, I scraped that off.
What does it start with?
Huh? That's called,
What's the first letter?
starts with a D. Okay, it starts with deposition. Oh, wait, no, it is deposition. It's called deposition. That one kind of makes sense because you have this gas that's depositing as a solid. So those are all the changes, but the way we've drawn it, right, you know that it takes energy to go from the solid to liquid and energy to go from the liquid to gas. Guess what? From the solid to gas requires energy. And then to go from the gas to the solid also releases energy. Because you know about exothermic and endothermic? So going up on this diagram, everything is endothermic. And then going down is exothermic. You have to release energy. So the process of making ice is actually exothermic. Going from the liquid to the solid has to release energy. And that's the job of your freezer. It's to remove the heat energy from the water to facilitate the process of going to the solid state. What's that?
Making ice is endothermic?
No, it's exothermic.
Exothermic.
Yeah. She was processing. Okay. So just some of the details in the melting process. What that energy does, right, is it allows the particles, the molecules of the solid, to partially overcome the attractive forces that hold the solid together, and then gives it enough energy that they can move around each other. Okay? It says move around a little and rotate. So actually what water molecules and all molecules of a liquid do, they're actually in the solution, they vibrate and they rotate and move around. Okay? We can actually measure all those things, by the way. You can measure their rotational frequencies and vibrational frequencies, all that kind of stuff. Now, when we go from the liquid to the gas, we'll talk about boiling here in a second. So when you heat a liquid, the vapor pressure of the liquid increases. Okay? Vapor pressure of the liquid increases. When you get enough energy. Let me do this. I'm going to skip part of this slide because I think it's kind of no fun. Let me do it like this. I'm just going to draw this. So here's a liquid. And I'm going to draw molecules on the surface. Here's my molecules on the surface. And then I have my heater. So that's the heat, that's this guy. And it makes fire. And so it's getting hot, right? So as I increase the temperature, what happens is the molecules in the liquid have enough energy to escape. So they're getting from the surface, they get bumped off the surface and then into the gas state. Okay? So this is the process of vaporization. As the temperature of the liquid increases, this vapor pressure increases. So why is it that the ones on the surface, right, can leave, but the ones inside can't? It's simply because the ones on the inside have things around them. They're stuck in the middle. When you reach 100 degrees Celsius, the boiling point of a liquid, for water, for example, then the vapor pressure is high enough that rather than escaping from the surface, they can just become the gas state inside the liquid. So that's why when you're boiling water, like on the stove, right? If you look at the bottom, where are all the bubbles coming from? They come from the bottom where the energy is coming in. What that means is that those gas molecules that are forming inside the liquid have enough vapor pressure to push the liquid out of the way. Right? So boiling, when it boils, this is a boiling. P of the vapor equals the atmospheric pressure. Whatever the atmospheric pressure is. And so that's how you can get a liquid to boil. That's what the boiling actually means. Like, I've asked this question before. Like when you see the bubbles inside of water, when you're boiling it, what's in the bubble? Who knows what's in the bubble? It's just water vapor. I've had all kinds of crazy answers in my life. But it's just water vapor, and it's there because the vapor pressure is high enough, it can go into the gas state and just push the liquid out of the way. Right? What if the pressure is higher? It takes more temperature, more heat, it takes more energy. If the pressure is higher, the temperature is higher. Okay? That's how pressure cookers work, actually. Pressure cooker allows you to cook food much more quickly because it's like a bomb. It's sealed, and you're boiling water in it, which is like a bad idea. And so the pressure goes up, and the temperature of the boiling point of the water goes up inside a pressure cooker. So you can cook a chicken in 10 minutes, 12 minutes. Once it starts cooking, once it starts boiling. Okay, so some other properties of liquids. One of them is surface tension. Now, the technical definition is kind of weird. Surface tension is the tendency for a liquid to minimize its surface area. For how many of you does that mean nothing? It means nothing to me. What does minimize the surface area mean, right? It means if it's the tendency for liquids, like without any other force on them, to form a sphere. Minimizing this minimum surface area is actually a sphere. So like in space, have you ever seen the astronauts when they do the little experiments with water? And they'll release some water, and it forms a perfect sphere. They've actually made them like this big before. And without gravity, water is perfectly round. If you take a high-speed picture of a water droplet, I should have brought some because that's one of my other hobbies. Take a high-speed picture of a water droplet, it's actually round. When it leaves, it looks like it's not round when it's leaving the faucet. So you have a faucet like this. That's my faucet. It leaves like this, right? But once it breaks away, it's a perfect sphere. It's almost a perfect lens, and you can take pictures through the water droplet.
Does that apply to rain?
Kinda, yeah. Anything. Anything that's a liquid. Hopefully it's water in the rain. This is Fresno area. You never know what's in the water. Yeah. So it's also, though, what's causing it is the forces of attraction. So, like, if you think about this is a water droplet, and then you think of water molecules on the inside, it's the attraction of the water molecules for each other that causes it to take that shape. So they're constantly pulling in on each other on the surface. Now, surface tension is also what creates on liquids essentially a skin on the surface of the liquid. So they show this picture here, right? And what's that in the picture? It's paperclip. And what is it doing? Floating. Now, what do you guys know about density? Density, if something's more dense, what should it do? It should sink, right? Well, that paperclip's made out of iron and chromium alloy. It's a mixture of iron and chromium, right? It's floating. The reason it's floating is surface tension. That is, the attraction of the molecules at the surface creates a skin on the surface that doesn't allow the paperclip to fall through. If you add a drop of soap to it, the soap will actually break the surface tension and it'll drop all the way through the surface of the liquid. One of the reasons we add soap to water when we clean stuff is to break up the surface tension. That, and it's good at removing fat and grease, but one of the reasons breaking up surface tension. Right. The stronger the intermolecular force, the stronger the surface tension. Okay? That's the kind of the bottom line. High surface tension, strong forces of attraction. And then, you know, weak means weak forces, a weak surface tension. Viscosity. Viscosity's definition is a little bit easier to understand. It's called the resistance to flow. Classic example is pancake syrup, right? Pancake syrup, motor oils, those are all viscous. Viscous. Viscous is resistance to flow. So it's the thick, a lot of people think of it, and this is still true too. It's thickness. It's how thick the liquid is. So pancake syrup, we would say, is a very thick liquid. Now, side note, how do you make it less viscous? Add soap, yeah. If you still wanted to eat it, you could add soap still. You heat it up.
Okay.
Right?
Oh, that's when I did
That's
that.
boring.
I heated up my pancakes and then they both.
Yeah, but you heat up the pancake syrup, right?
Yeah, it got hard.
Because what it does is what does heating do for the molecules?
Breaks them up.
No.
Why does it break them up though?
Because they shake faster.
They shake faster. They have more energy. So if you add heat to like pancake syrup, what you're doing is actually making the molecules vibrate faster, and then they can flow better past each other. So they're not stuck together, right? You heat them up, they're vibrating more, and as you pour it, it can flow past. So a molecule of sugar is what it really, pancake syrup is just pure sugar. Molecules of sugar can flow past each other more easily. So yeah, surface tension and viscosity both behave this way. If you want to lower the surface tension, you can heat the liquid up. If you want to lower the viscosity, you can heat the liquid up because you break up the interactions between the molecules. All right. High viscosity, high strong forces of attraction. I talked about this. Just go over the slide a little bit. Escaping from the surface, known as vaporization or evaporation, right? Those are the same thing. Liquids can escape from the surface more easily if they have weaker forces of attraction. And if they have stronger forces of attraction, it's harder for them to leave from the surface. This is called the vapor of the gas. And high vapor pressure means weak forces of attraction. It's kind of the opposite of, like when we're talking about highs and lows, it's the opposite of viscosity and surface tension. High forces of attraction mean high viscosity, high surface tension, but it means low vapor pressure. And then if I have low vapor pressure, it's high attraction. And vapor pressure, just like viscosity and surface tension, is affected by temperature. You can increase the vapor pressure by increasing temperature and decrease it by decreasing the temperature. Now, it's actually on the next slide. I'm just going to write it right here. If it has a high vapor pressure, and this is a term used for liquids, we would say it's volatile. Like when you say somebody is volatile, what does that mean? They're like reactive and they're angry and they spout out. That's what volatile means. They're just very emotionally like on the edge all the time. And so liquids that are volatile have high vapor pressures. Liquids that are non-volatile have very low vapor pressures. Okay. And I just said all that, so I'm going to pass it. And I'm going to skip this too, but it is written right here. It says, eventually the temperature is high enough for the molecules in the interior of a liquid to escape a phenomena escape into the gas phase, a phenomenon we call boiling. And you'll notice, like in this pot, when I blow it up, that's where all the bubbles are coming from, right? Anybody ever put a 2-cup measuring cup of water in a microwave and actually look to see where the bubbles come from? The middle and the top. Like when you boil water in the microwave, because the energy source is at the top, the bubbles don't come from the bottom. They come from the top and the middle of the liquid.
The middle?
Yeah, because it's absorbing energy, and eventually the bottom is the coolest part. Kind of weird to think about. Now, the really dangerous thing that you probably shouldn't do is you could put liquid in a microwave and get it to above its boiling point, and it won't boil. And then if you like just watch it for a while, it'll explode in your microwave.
That's a great
Will it
idea.
mess up your microwave?
Probably.
I think my mom would.
I've only done it a few times, but I'm telling you not to do it because it is kind of dangerous. Your teacher could do it for you.
Miss Campbell.
Wait, we'll put a thing of water.
You know how it usually happens to me is I'm usually boiling water in my microwave to make coffee. And I'm not paying attention. And I'll open up the microwave and I'll grab it and it'll just go brrrr. I'm like, well, that was really cool.
Okay, it's really-
Yeah, don't do it though. It's very dangerous. Let your teacher do it.
Your mom would get mad.
He's lived a long and prosperous life. Wear a glove, that's all.
Burned myself enough times.
Yeah. This is what chemists do. You know what alchemists, you know what the sign of a successful alchemist used to be? How many fingers he was missing. You know why? They would stick their finger in their solutions and stir it.
Why?
Because they were alchemists. They're trying to make lead into gold. What do you expect? I mean, anyways. Yeah, a successful alchemist was often missing fingers. Okay, so let's talk about boiling point real quick. The higher, right? The boiling point, the more energy it takes the forces of attraction to break the forces of attraction between molecules. So high boiling points, strong forces of attraction. Likewise, low boiling points, low forces of attraction. What about freezing point? What is freezing and melting, right? You're going from solid to liquid, and you need to break up the forces of attraction. So if the forces of attraction are strong, what does that mean the melting point's going to do? It's going to be higher because it takes more energy to break them apart. So like for liquid, going to the gas state, just like for boiling, the forces of attractions are strong between the molecules. In order to get it to go to the gas state, you have to be able to break those forces of attraction. Stronger forces of attraction, higher boiling points. Similarly, when you're going from the solid to the liquid, right? You have to break the forces of attraction between the molecules of the solid to get them to be in the liquid state. The stronger those forces of attraction are, the higher the melting point. Okay? And so you'll see on the next slide, oh, it's not on the next slide. Did you not have it? Oh well, I just said it, melting point. Stronger forces of attraction. Higher melting point. He summarizes it all on this slide. This is Mr. Samora's slide. I'm just going to skip this, but you guys can go through and read the summary. It's a summary of everything that was on the previous slides. All right. Okay, so let's do this. Oh, it has all the answers on it. I thought I deleted all those. Dang it. What? Sugar, sugar. I don't know what you're thinking about. Sugar, sugar, water, water, ice, ice?
Yeah.
Could make a chant out of it. Okay, let's explain why though. Okay, like why we know that's true. It says pick the substance in each pair with the stronger intermolecular forces of attraction. Now you look at sugar at room temperature. You're looking at sugar, and you're looking at water. What state is sugar in at room temperature? And water is a, so it means the solid has stronger intermolecular forces of attraction. That's why it's a solid. So that's how we know for sugar or water, sugar has the stronger intermolecular forces. Now you guys don't know about water and acetone probably. Do you know what acetone is? Nail polish remover. Like when my daughter, because I actually don't do fingernails, but when my daughter does her fingernails in her room, guess how I know? I can smell it.
My
So
house is the same thing.
acetone is very volatile.
It's very toxic too.
It's not that bad. So, well, yeah, there's worse. But acetone is very volatile. Things that are really volatile that get to the gas phase easy have weak forces of attraction. Right? So that's how we know between water and acetone. Just our experience with fingernail polish remover and my daughter tells me that acetone has weaker forces of attraction than water does. Okay. What? We'll talk about structure, like intermolecular forces. We'll talk actually like what the structure means and how we can compare, use structure to do this too. So ice or dry ice? Why? Because ice melts at a much higher temperature than dry ice sublimes. Dry ice is really cold when it sublimes, right?
What temperature would you dry ice melt?
All I know is if you, actually this is weird information. If you take acetone and you mix dry ice into it and make a solution out of it, it's minus 78 degrees Celsius. So I don't know if that's close to its melting point or not, but I think it's close to it. Yeah. Acetone doesn't freeze at that temperature. You can put dry ice into it and stir it right. Put it in water, it'll just freeze. But dry ice and acetone. It's actually a common mixture that people use in labs to get really cold. Yeah, acetone, dry ice, minus 78.
Would that work with rubbing alcohol?
If it's pure, it probably would. If it has any water in it, it'll probably freeze the water out. Probably. Not positive. Okay. 10-minute break. And then we're going to finish this chapter and be done.
Yay.
And then did it unpause?
Yeah.
Yeah, it did. Oh, and I did put one of these up on YouTube yesterday, but it didn't process when I was watching it upload. So as soon as I see the links active, I'll give those to you guys. Okay. I don't know what you're going to really hear listening to it again, but maybe you miss it. Okay. So why are there dispersion forces? It's something called the instantaneous dipole. Okay, so let me ask you a question. Helium atoms are charged or neutral?
Neutral.
Neutral. Why are they neutral?
To
Because they have 2 protons, helium, and 2 electrons, so they're neutral, right? Now, here's the thing. The electrons are around the nucleus in a cloud.
Yep.
So they're not fixed in place, right? So, who wants to be a nonpolar molecule? Who has? Oh, come on, nonpolar molecule. I forgot your name again.
My name's Madison. Mad. So mad. Mad Dog.
Mad Dog?
She's had a lot of nicknames.
All right, Mad Dog, let's go. That's like a sports nickname. I can remember those
Water
things.
polo. We call it water polo.
Or what?
Mad Dog. Remember
Mad
that?
Dog? Okay, so, you're nonpolar. These are your electrons. You're nonpolar. What are you going to do? Where are your electrons? Are they like this? No, don't look at that. You're nonpolar. These are electrons.
Okay.
What do electrons do? They don't like electrons, so they repel, right? So where are your electrons going to do?
They're gonna go this.
They're going to go like this or they're going to go like this?
Go apart.
Okay, so now watch this. Where's your positive charge?
We'll say this is positive.
No.
It's in the middle.
It's your head. Are you sure?
Sure.
You just say I'm positive.
Positive.
Okay, your head's a positive charge. So here's the negative charge. Now watch what happens when I come up next to her.
Go work away.
What's going to happen? What's her negative charge going to do? That negative charge has to move. Oh, now what's left? Look at it, hit you. It was looking. Right? See what happens? Now there's a force of attraction. So now if I move away, she's not there anymore, right? So what are we going to do? We're going to go like this. The electrons are around, right? And then we get like next to each other. And then if she does that, then I'll go like this again. But if I do this, what does she do? She punches me in the head. Do it. Because we'll do the demo one more time. You get it? So this is what's called an instantaneous dipole, because a dipole is a separation of charge. And so what happens is, her electron has a watch. When we go like this, and then hers moves away, see what happens? Her positives here, her negatives over there. Creates a dipole. And so these, okay, you can sit down again. Mad Dog. All right, Madison. I'll stick with Madison. I just work with whatever. This is what this diagram means. Right? You start with the electrons sort of randomly dispersed around the atoms, but when they get next to each other, the electrons have to move, and that creates a force of attraction. All right. So you can see the dispersion force. You can see the dispersion force in these numbers. So we have helium, we have neon, argon, krypton, and xenon. Those are all the noble gases, except for I don't know why they didn't do radon, probably because it's radioactive. They had all those noble gases. And then you look at their boiling points. Helium's boiling point, minus 4.2 degrees Kelvin. Right? But xenon's 165 degrees Kelvin. Even though that's still really cold, because induced dipoles are a very weak intermolecular force, it's much higher than the helium's. So why did that happen? The trend is because as the molar mass increases, right, the induced dipole increases, you have a stronger force of attraction here. And a weaker attraction here because the mass, or the trend is the mass. So then the question is, why is the attraction stronger when the mass is higher? Why is the force stronger when the mass is higher? There's more what? More electrons.
Space.
Yeah, so you have more. What does this mean? She's like, the sun. Right? That's what you do when you do the sun? No? The face?
Yeah.
Yeah. Bless you. I have to call doctor. So, the more electrons you have, the more you can move, and the bigger the induced dipole. So the more electrons, the bigger the induced dipole. Okay, I'm going to teach you one other thing that's not on here. So let's say we have a molecule that looks like this. And we have a molecule that looks like this. Because this is another important principle of these kinds of structures. Let's see, 1, 2, 3, 4, 5, 6, 1, 2, 3. Oh, I got to get rid of one. Got too many. These are known as hydrocarbons, just because they're made up of carbon and hydrogen. How many carbons in the top molecule? 5? Yeah, 5. Sorry, I drew it. I didn't even count. How many in the bottom? 5. Okay. How many hydrogens in the top one? 12. Okay. Yeah, it's 12. What about the bottom one? What? No, it's 12. It's 12. So these are known as isomers of each other. They have exactly the same formulas, right? But the structures are different. Here, this is known as a branched alkane because it has a branch on it. But they're exactly the same molecular weight. So based on what you know now, right, molecular weight being important, which one of these has stronger intermolecular forces? But they're the same. We just figured out that the same carbon, same hydrogen.
Oh, so then
Turns out it's the top one. Yeah, right? This is stronger. I'm going to call it IMF, intermolecular force. I'm going to abbreviate it that way. Here's the reason why. The more places they can stick together, the stronger the force of attraction will be, the net. So if it's a long molecule, it'll stick together, right? And there's more surface area contacting, and it'll stay stuck better. That's why a long strip of Velcro versus a short strip of Velcro, right, holds things stronger. Right? The other thing, this is where I typically experience this, is wrapping Christmas packages. You ever wrap Christmas packages? And then you take out little pieces of tape, and then two pieces get stuck together, and you just take them apart, and then you keep going. But then you say, oh, I'm going to save time. And you get that big long piece, and then you lose control of it, and the whole thing gets stuck together, and you can't get it apart anymore. It's the same reason. You have all this surface area stuck together. It's really hard to separate. So this is actually very important for larger molecules. The length of the molecule longer makes a stronger net intermolecular force. And so boiling points will be higher, melting points will be higher, things like that. Okay. All of these are nonpolar. First qualification. Pick the substance in each pair with a higher boiling point. And why? C3H8, why? Huh? It's heavier, got more mass. More mass, more electrons, right? So it's this one. It's also longer because it has 3 carbons in a row. So there's a number of reasons why, but this is higher mass, stronger force of attraction, right? And the question really is boiling point, means higher boiling point. BF3, BCl3, which one has a higher boiling point?
CL3.
Yeah, BCl3.
Yeah.
Why?
Bigger mass.
Same thing I wrote up there, right? Really, this question is asking which one has stronger intermolecular force. You pick that, and then you know which one has the highest boiling point. Okay? Sorry, I was thinking Battlefield. Sorry. I play too many games in the summer. Okay, CO2 versus CS2.
CS2.
Yeah, CS2 because of the same reason. Higher molar mass, stronger intermolecular force, higher boiling point. Counter-Strike. Next. The next type, so the induced dipole is the weakest kind. The second type of intermolecular force is the next strongest kind of intermolecular force. And that only exists in molecules with dipoles. So one of the things you're going to have to be able to do is know what the structure of a molecule is, right, and be able to tell whether it's polar or nonpolar. So polar molecules have a positive end and a negative end. So this is actually a drawing of formaldehyde. It's this. It's not a drawing, it's a model of formaldehyde. And oxygen has a much higher electronegativity than carbon. So this is the negative end, and this is the positive end. And so that's what they're showing right here. A dipole-dipole interaction is this interaction right here. Dipole, and they often say dipole to dipole to be really clear, but most of the times we can just get rid of the two and just say dipole-dipole. It's the dipole of one molecule interacting with the dipole of the other. The bigger the dipole, okay, the stronger the force of attraction. Typically things sort of medium intermolecular weight, we're talking like in the range of maybe 20 to 30, have boiling points from about -20 to 60 degrees Celsius. So it's a moderately strong intermolecular force as opposed to dipole, induced dipoles, which are considered to be weak. So here's a bunch of different molecules, right? And what they've done in these molecules is they've actually measured the dipole in a unit called a debye, and we don't have time to talk about what a debye is. But a debye is sort of like a measurement of how big the separation of charge is. So like 3.9 debye, 3.9 D for this compound down here, which is known as acetonitrile. This is acetonitrile. This is 3.9. It's much more polar than, for example, this. That's known as dimethyl ether. So, what does that mean? All right, the bigger the dipole, the higher the boiling point. So the stronger the intermolecular force of attraction, again, higher boiling point. Now, how do you know what the dipole size is? You guys, this is experimentally measured. They actually take an instrument and they measure oscillations of electric current through two electric. It's a weird, complicated measurement. But here's the deal: you guys can't do that. So how do you do it? You do it based on electronegativity. The bigger the electronegativity difference, the bigger the dipole. Okay. So yeah, this column on the right, you couldn't reproduce unless you did it experimentally, or were given data to do it. But you can do it based on electronegativity differences. Okay. Now, to determine whether or not something has, right, a dipole, go ahead.
Is it possible for something to have the same molecule, same number and type, but have a different structure? Can it be structured differently?
Yeah. So you could have, so what you're actually asking about is a general category called isomers. Isomers, same chemical formula, different structure. So there are actually left-handed versions of molecules and right-handed versions of molecules. They're mirror images of each other. Those are stereoisomers. And then there's constitutional isomers, like the one I drew up here, with the CH3s, the 5 carbons. those are constitutional isomers. The way they're attached to each other is actually different. Yeah, whole stereoisomers is how you know the difference between like spearmint and rye bread. Like rye bread, like caraway. You know what caraway is? Like rye bread? It's horrible stuff. I hate it. You guys know what caraway is? Like rye? Rye bread? They make, they'll make Reuben sandwiches on them.
Oh, yeah.
Yeah, and that's the classic bread for that is rye bread, which I hate. So I always do it on sourdough. But anyways, long story. But caraway and spearmint are the same molecules, but they're mirror images of each other. And the reason they taste different is because all the receptors in your body, right, are shaped differently. If you think about the way you taste stuff, it triggers flavors in your mouth or the things that you inhale. You have like these molecules that are handed, like right hand, like you'll notice my right hand and my left hand are different from each other, right? They're mirror images, but they're not the same. So you have this molecule that's shaped like this, and it goes up inside, it's a weird visual, goes up inside your nose, and grabs onto a receptor, and it's like, oh, that's spearmint. It sends a signal, it activates a receptor that activates a neurochemical pathway that triggers a signal that goes up into your brain. And then you say spearmint. If you take your other hand, I mean your other molecule, and you stick it in the same spot, it won't fit. Because these are oppositely shaped. If it takes this as the code, it can't take that as the code. Because they're different handed. So you stick this in your nose and all of a sudden you're like, caraway, I hate that stuff. I'm going to do sourdough instead.
Oh.
That's exactly what I do. Yeah. Yeah, so shapes of molecules are really important. You learn this. If you take biology, are you guys all plant science?
Yes.
Yeah. So my sons are working for the USDA. They're doing their PhDs in ag research. And what they're doing is, so you think, farmers or whatever, and I grew up in the farm. They're actually designing the molecules that they use to trick insects into thinking like something else is going on. And that involves shapes of molecules or types of classifications of molecules like esters, fruity smells. They're working on all that kind of stuff, and then ways to release it out in the field so that it is only available in the times that you need it to be.
So IPM.
Huh?
So IPM.
IPM, what is that? Integrated pest management? Yeah, exactly. But they're on the developmental end of creating the molecules that people will use in the next generation. And they're doing fumigation treatments, like they do the whole 9 yards. They have a fumigation tent that they can drive a truck into and they close it off so post-harvest in the field stuff. They're working on fumigations for cars going to Australia. I mean, it's like this kind of research, like ag-based research, is like all over the world, jobs everywhere. So anyways, I'll stop talking about that. Oh, and internships right here in Parlier. Just a thought. That's how my sons got into it. I knew a guy over there. My sons needed something to do for the summer. I go, hey, you should send a resume over there.
Yeah, we're doing internships after this class.
Oh,
Like,
yeah.
some of us have NFL and hacking.
Yeah.
Like, we
Yeah.
have NFL and hacking.
But if you can go to the USDA, then you're doing like high power research, like stuff, because they're doing it through. My sons are getting their PhDs through UC Davis. Ah, yes. Okay, I'll stop advertising. But they got a lot of people doing stuff out there. Okay, I'll stop. One more thing. And you think like, oh, but I'm going to be stuck in the valley all summer long. So one son is going to Michigan for the rest of the summer. I think the other one's going to New Hampshire. Because the USDA is all over the United States. They're working on specific projects that are problems in lots of places. And then the other one, my third oldest, so K3 is what he's known as. K3, he's going to go to Michigan, and he's only a sophomore, so he's only like 2 years older than you guys. He's already done a summer of research in Michigan. Now he's going to go back, and then he doesn't want to do this, but he might get to go to Alaska for the end of the summer. So like, I'm just saying, you're talking about like, I'm going to do ag research, but I want to do an internship. You don't have to be here. You could be all over the United States. Anyways, Okay, now I will stop talking about it. Okay, so in order to, and part of it, they had to learn all this. So part of what you need to know is to determine whether or not something has dipole attractive forces. So we're going to talk about CS2, right? All right. So if I drew the Lewis structure, it looks like this. All right, so sulfur's electronegativity is 2.5 and carbon is 2.5. Polar, nonpolar, ionic.
Polar,
Nonpolar. Carbon and sulfur, same electronegativity. This molecule is nonpolar. Does it have dipole attractions? No, because it's nonpolar. Okay, let's do CH2F2, right? So if you do the Lewis structure for CH2F2, it's going to look like this. It's actually tetrahedral. Looks like that. Now, carbon and hydrogen, this bond, I'll just tell you up front, it's nonpolar. Difference is 0.4, but this one is polar. The reason it's polar because it's 4.0 minus 2.5, so that's 1.5. And remember, between 0.4 and 2, that's polar. So this molecule has polar bonds. And it's asymmetric. And if you remember what I talked about the other day, if I had fluorines at every place and it was completely surrounded by fluorines, it would be nonpolar. But because this has polar bonds and is asymmetric, this molecule is polar. And it will have dipole-dipole interactions. Now, CF4, you can already guess what that one is, maybe. Looks like this. I'm not going to draw the lone pairs just for sake of time. And actually, we usually don't. In organic chemistry, we usually don't draw the lone pairs. Bonds are polar, but you notice how there's a fluorine at every point? So that molecule is symmetric. So this is nonpolar. So the only one of these three that has dipole-dipole interactions is this one. I'm going to show you one other. It's one of the common nonpolar molecules you'll see on tests often. CO2. That's what carbon dioxide looks like as a Lewis structure. You guys drew it yesterday. The bonds for CO2, electronegativity of oxygen, that's 3.5. Carbon, 2.5. So the bonds are polar. There's a difference in electronegativity of 1.0. That molecule, polar or nonpolar? Bonds are polar, but you notice how the molecule is symmetric? So it's nonpolar. Okay? Bonds are polar, but the symmetry means that you have equal negative charge on the left side and the right side. And so the molecule is actually nonpolar. Okay. Last one. This is the strongest force of attraction. It's called hydrogen bonding. In order to have hydrogen bonding, you have to have hydrogen and fluorine, oxygen or nitrogen bonded to hydrogen. Okay? So examples of molecules that have hydrogen bonding, HF, H2O, benzyl alcohol. I don't even know why that's in there. This is ethanol, ammonia, right? Do you recognize? Oh, I didn't mean to circle the whole thing. Sorry. I just meant to circle this part, and this part, and this part. Specifically, it's the part of the molecule that has the nitrogen with the hydrogen, or the oxygen with the hydrogen. If you have those things, you have hydrogen bonding, okay? High boiling points, like water's boiling point's 100 degrees Celsius. That's relatively high for such a small molecule. The hydrogen bonding interaction is usually drawn as a dashed line like this between the hydrogen on the oxygen, so this guy, and the lone pair that's on the other oxygen. So often, like you'll have like O, like we do it in a Lewis structure, H, and there's something else over here. You'll have another oxygen here with a lone pair and an H, like this. The hydrogen bond is this interaction right there. It's roughly, in terms of strength, about 10 times stronger than a dipole-dipole interaction. So it's significantly stronger, and that's why the boiling points are so high. Ooh, what happened? Whoa, I zoomed like crazy. Didn't mean to do that. Yeah, so just some examples. Ethane and ethanol, molar masses are roughly the same. So their dipole-dipole and their induced dipoles are the same. Oh, actually, this is methanol. I thought that sounded weird. This is methanol. Let me spell it so you can read it. Zoom it in. Methanol. There we go. So, ethane, right, just is a hydrocarbon again. It's nonpolar, only has induced dipoles. Its boiling point, minus 88 degrees Celsius. Methanol, it's about the same molecular weight, has hydrogen bonding because of this OH group. Its boiling point is 64 degrees Celsius. 65 is usually what we accept. I end up having to boil it all the time in organic chemistry. 65 degrees Celsius. So roughly 100 degrees-ish higher. 120-ish. But it's much, much higher just by having hydrogen bonding. The boiling point is much higher. It also affects other properties, like the ability to be dissolved in water. Water has hydrogen bonding in it. Right, so there's hydrogen bonding. To the lone pair on the oxygen. And it turns out if you want to make a solution out of water, the things that dissolve the best are the things that have hydrogen bonding. Okay? Because the forces of attraction are strong and they tend to like each other and pull together as a solution. Oh, let's see. Yeah. So given some structures here, right? Which of the following is a liquid at room temperature? And the other two are gases. So I have formaldehyde. I have fluoromethane. And I have hydrogen peroxide, right? So if you go through, you do the analysis, the molecular weights are all about the same. Formaldehyde is polar. What are you doing?
Sorry, they printed out the slides and it's so messed up.
Oh yeah, because what they did is they printed this slide on top of this slide.
Yeah.
Yeah, I separated it out. That way you could see it. I'll post this. I posted it yesterday, the ones I wrote off. Those, do you guys find those? We're getting an announcement that I posted the slides. Oh, under the modules now, if you go and you look at the bottom, there's the one called lecture notes. And I'm posting what I write. So I'm recording it on YouTube and then I'm posting this so you can go back and look at it. So formaldehyde, right? Yeah, so don't try to look at the slide, it's a horrible mess. Formaldehyde's 30 grams per mole, fluoromethane 34, and then hydrogen peroxide is 34.02. Formaldehyde and fluoromethane and hydrogen peroxide, they're all polar, right? So they all have dipole-dipole interactions. But the only one that has hydrogen bonding is which one? Is this one, the hydrogen peroxide. So the one that's a liquid at room temperature is the hydrogen peroxide. It has the strongest intermolecular force, and the other two unless they're dissolved in water. That's the only exception. The other two are gases at room temperature. Okay, so the hydrogen bonding of the hydrogen peroxide is what allows it to be a liquid. I'm going to show you one other kind of cool thing. Gosh, there's a little bit more, and I really don't want to do this right now. I'll do it tomorrow. But I want to show you one other thing, so I'm going to stop here. This is sort of a summary of the intermolecular forces, so you can look at that on your own. But one last thing I want to talk about. So Jackson said earlier, so I'm blaming it on you, and then we're going to go for lunch, and then we'll do that. Okay, so, but he said, hey, are there any other substances that what? Remember?
Form a solid that's less dense.
That form solids that are less dense than their liquid state. You guys know ice is less dense than water.
Yes.
Did you know that?
No.
Yeah. Ice is less dense than water. That's why you take an ice cube and you stick it in water, it floats. Okay? So why does it do that? Why is ice less dense than the liquid state?
Because it freeze with bubbles inside of it.
No, not because of freezing. You can freeze it. Okay, you're my guinea pig. Come up here. Actually, I've done this with whole classrooms before, but I don't think I want to do that just yet. So come on, guinea pig. And Jackson, since you brought it up, you're the other guinea pig.
Are you gonna freeze them?
We're gonna freeze.
Okay.
We're gonna make an ice crystal. Jackson, come on.
How long are you doing it?
Unfortunately, the height discrepancy may be a deterrent, but that's okay.
I know he's shorter.
Yeah. Okay.
Okay, what am I doing?
Well, you're a water molecule.
Oh, okay.
You're not a water molecule. No. Yes. Why did he have to bend his arms?
Because it's the best shape.
Because it's a bent shape. Water is bent. So you're a water molecule, and I'm a water molecule. Okay. So now we're in the liquid state. Good.
That's great.
We're in liquid state.
Good job, Jack.
And we can actually kind of, oh yeah, we're doing a ballet. And then now who wants to be the cold? Who wants to be the cold?
I do.
No. It's one of you has to be the cold.
Oh, Hayden.
Hey,
Come on, Hayden.
Hayden. No, you have to do this. You're cooling us off. Right? And so we're going to lower in energy. So now what happens is, what's happened right is our intermolecular forces become important. And we're going to start hydrogen bonding. I know it sounds a little, but we're going to hydrogen bond. Hydrogen bond on the stage here. Now where are your lone pairs?
Oh, God.
Some of you, we're bent, right? You said we're bent. So the hydrogens are this way. We're
Oh,
in the lone
behind
pairs.
me.
They're behind me. So I like go up to you like this. We're going to hydrogen bond.
Okay.
You get it. Okay, we're going to turn around. And he's going to stick a fist towards my back. But here's the deal. The electrons are a lone pair and they stick out, right? So in order for this to be just the right way, I got to step away from it. Because, and then you got to turn around too. You're part of this. You got to be cooling the whole thing off. Right? So what happens when we cool down?
You get closer
Turn that way.
together.
There we go. No, we actually have to move. So here's the deal. We actually have to move apart so we can line up our hydrogen bonds. Otherwise, we can't line up our hydrogen bonds. And the hydrogen bonding effect is like 10 times stronger than the dipole effect. And that's why it expands and is less dense as a solid.
That makes sense.
Yeah, and water, go ahead.
Okay.
Water is the only substance that has such high hydrogen bonding that it forces the solid to be less dense than the liquid when the hydrogen bonds form. Yeah, you can imagine the chaos with a whole classroom full of students doing this.
Yeah.
It's fun though. I did it with teachers, elementary school teachers. It was fun. Yeah. All right.